least 56 feet away from the point from which the waves are reflected, for then the second blow will come 1/10 of a second after the first one, and this is long enough for you to feel them separately. Miss C. A. Martineau tells a story of a dog which was terribly frightened by an echo. Thinking another dog was barking, he ran forward to meet him, and was very much astonished when, as he came nearer the wall, the echo ceased. I myself once knew a case of this kind, and my dog, when he could find no enemy, ran back barking till he was at a certain distance off, and then the echo of course began again. He grew so furious at last that we had great difficulty in preventing him from flying at a strange man who happened to be passing at the time. Sound travels at 1120 feet in a second in an air of ordinary temperature, and therefore 112 feet in the tenth of a second. Therefore, the journey of 56 feet beyond you to reach the wall and 56 feet to return will occupy the sound wave 1/10 a second and separate the two sounds. Sometimes in the mountains, walls of rock rise at some distance, one behind another, and then each one will send back its echo a little later than the rock before it, so that the ha which you give will come back as a peal of laughter. There is an echo in a Woodstock park which repeats the word 20 times. Again, sometimes, as in the Alps, the sound waves coming back rebound from mountain to mountain, and are driven backwards and forwards, becoming fainter and fainter till they die away. These echoes are very beautiful. If you are now able to picture to yourselves one set of waves going to the wall, and another set returning and crossing them, you will be ready to understand something of that very difficult question. How is it that we can hear many different sounds at one time and tell them apart? Have you ever watched the sea when the surface is much ruffled and noticed how, besides the big waves of the tide, there are numberless smaller ripples made by the wind blowing the surface of the water, or the oars of a boat dipping in it, or even raindrops falling? If you have done this, you will have seen all these waves and ripples cross each other, and you can follow any one ripple with your eye as it goes on its way undisturbed by the rest. Or you may make beautiful crossing and recrossing ripples on a pond by throwing on two stones at a little distance from each other, and here, too, you can follow any one wave on to the edge of the pond. Now just in this way, the waves of sound, in the manner of moving, cross and recross each other. You will remember too, different sounds make waves of different lengths, just as the tide makes a long wave and the raindrops tiny ones. Therefore each sound falls with its own particular wave upon your ear, and you can listen to that particular wave just as you look at one particular ripple, and then the sound becomes clear to you. All this is what is going on outside your ear. But what is happening in your ear itself? How do these blows of the air speak to your brain? By means of the following diagram, figure 33, we will try to understand roughly our beautiful hearing instrument, the ear. First, I want you to notice how beautifully the outside shell, or concha as it is called, is curved round so that any movement of the air coming to it from the front is caught in it and reflected into the hole of the ear. Put your finger round your ear and feel how the gristly part is curved towards the front of your head. This concha makes a curve much like the curve of a deaf man makes his hand behind his ear to catch the sound. Animals often have to raise their ears to catch the sound well, but ours stand always ready. When the airwaves have passed in at the hole of your ear, they move all the air in the passage, which is called the auditory or hearing canal. This canal is lined with little hairs to keep out insects and dust, and the wax which collects in it serves the same purpose. But if too much wax collects, it prevents the air from playing well upon the drum, and therefore makes you deaf. Across the end of this canal, a membrane or skin called the tympanum is stretched, like the parchment over the head of a drum, and it is this membrane which moves to and fro as the airwaves strike on it. A violent box on the ear will sometimes break this delicate membrane or injure it, and therefore it is very wrong to hit a person violently on the ear. On the other side of this membrane, inside the ear, there is air, which fills the whole of the inner chamber and the tube, which runs down into the throat behind the nose and is called the Eustachian tube after the man who discovered it. This tube is closed at the end by a valve which opens and shuts. If you breathe out strongly and then shut your mouth and swallow, you will hear a little click in your ear. This is because in swallowing you draw the air out of the Eustachian tube and so draw in the membrane, which clicks as it goes back again. But unless you do this, the tube and the whole chamber cavity behind the membrane remains full of air. Now as this membrane is driven to and fro by the sound waves, it naturally shakes the air in the cavity behind it. And it also sets moving three most curious little bones. The first of the bones is fastened to the middle of the drum head, so that it moves to and fro every time this membrane quivers. The head of this bone fits into a hole in the next bone, the anvil, and is fastened to it by muscles, so as to drag it along with it. With the muscles being elastic, it can draw back a little from the anvil, and so give it a blow each time it comes back. This anvil is in turn very firmly fixed to the little bone, shaped like a stirrup, which you see at the end of the chain. This stirrup rests upon a curious body, which looks in the diagram like a snail shell, with tubes coming out of it. The body, which is called the labyrinth, is made of bone, but it has two little windows in it, one covered only by a membrane, while the other has the head of a stirrup resting upon it. Now, with a little attention you will understand that when the air in the canal shakes the drum head to and fro, this membrane must drag with it the hammer, the anvil, and the stirrup. Each time the drum goes in, the hammer will hit the anvil and drive the stirrup against the little window. Every time it goes out, it will draw the hammer, the anvil, and the stirrup out again, ready for another blow. Thus the stirrup is always playing upon this little window. Meanwhile, inside the bony labyrinth, there is a fluid-like